So good morning, everyone. Our first speaker today is Seis, and he will be speaking on mixing by randomly moving vortices.
Yeah, thank you very much. Thanks for coming in on Saturday morning. I appreciate it. Yeah, what I present is joint work with two persons from Münster. Victor is a PhD student, and he will start at the Imperial in the Vortices group in September as postdoc. And then there is André Schlichting, which is a colleague of mine. I persuaded him in the past year, but mixing is very interesting. So it has like general introduction. We've seen lots of things already in the past talk, in particular in Anna's first presentation. Anyhow, I will just recap a little bit. So we're concerned with the fluid, and there are basically two ways to mix. And the one possibility is that we have a flow, that convection, which leads to filamentation. This is the upper picture. And so this filamentation leads to a reduction of scale. I think this is quite obvious here, and this is what we all know. And the other possibility is when we have a diffusive quantity, like temperature, or maybe some, I don't know, some mass densities also, when there's really a proper diffusion, not just conduction, like chemical collapse or so, then we could also have a reduction in the intensity. So diffusion works on gradients. If there are sharp gradients, then diffusion smooths this out the interface. Okay, so these are the two possibilities, and the model behind that is what we've already seen before. This is just a linear model here. Theta is the transported quantity, so temperature, concentration, mass, or whatever, and use the velocity fields. And here kappa is the diffusivity constant. It might be 0 depending on the situation that I consider. Therefore, I write it this way. And the velocity will always be divergence free for simplicity. Probably also many constructions will work as well. So I'm considering the bounded smooth domain in this case, and in order to ensure that theta is a preserved quantity, we have to assume that U and gradient theta have free or no flux boundary conditions, and here I also write it with a kappa in order to stress that these boundary conditions would only be relevant if kappa is positive. Otherwise, we cannot prescribe boundary conditions for the transfer function. Okay, so what else is what do I also always have in mind? So it's on a mathematical level, it's not important, but I always think that of theta being like some quantity in a bounded quantity, so say between -1 and 1. It's not really important, but just all the pictures that I'm drawing are motivated by that. The R2 norm then is order 1, means it's not mixed, and there are no small structures, yeah, so that the gradient is of the same order. That's what I'm assuming. This is the picture here. Yeah. So interface is order 1, and in most of the time, we're just having these ±1 blanket situation. Okay, so the next situation is that I'm always assuming that we have a regular velocity field, in the sense that the velocity is Sobolev. So I always assume P larger 1 when I talk about results in the following. I mentioned yesterday for some of the fact that we are studying P equal to 1 is still open. And if I have such a situation, and so in particular, if the interface is quite smooth, then the diffusion in the very beginning is not very efficient. So there are no gradients to smooth out. And therefore, in such a situation, initially, advection is mixing, or is the process of the mechanism which is mixing on a much more efficient scale than the diffusivity. And so, like if I envision we have a turbulent situation, then we have first a reduction of scale, and yeah, as I said, diffusion is not very important. And then there's a certain scale which is called the Bachelor scale, in which diffusion and the filamentation, the advection would balance, and from then on, I would expect that diffusion becomes dominant, because then even if I mix or if I stir and if I create finer filaments, they are eaten up immediately by the diffusion. So this is a little bit the heuristic picture that. Anyhow, so in this talk, we are concerned with quite regular fields. Yeah, so it's not a it's not a turbulent situation. Anyhow, I want to study the effect of vortices on mixing, and I mean you see them everywhere in nature. Yeah? So if you study fluid dynamics, you have these coherent vortex structures which move according to the Euler equations essentially, and maybe around them there's some turbulence, maybe there's nothing happening, yeah, but you observe these structures everywhere. And okay, so when I speak of a vortex, I might not actually mean a vortex, because for me a vortex is something in which the velocity is decaying. I would love to deal with these situations as well, but currently we have what we can do is situations in which the velocity is increasing away from the vortex. I can comment on that. I believe that also the other situation will be true for what we do, but actually, when I mean a vortex, I mean maybe something like this. So. Okay, so let's start with a purely advective case to fix ideas. And also because, as I just motivated, I think initially this is really the dominant situation. So let's study the transport equation. Yeah, it's clear that if you test with theta integrate by parts, that the L2 norm, but also any LP norm is preserved. That in the language of the Penanions, that would be called renormalization. And therefore, mixing can only happen by the reduction of scale, and we also discussed this. We measure this in terms of negative superlatives, and among them, the H-1 norm is just the one which is most frequently used, probably, and I think it's for two reasons. So one reason is that often it has a very nice presentation, and it scales like a length. Yeah, so therefore, as Anna also said, the H-1 norm is really the average, or measures the average length. It scales like the average length of your system. So in our case, we have a bounded domain. So I do an eigenvalue decomposition here, so to say, I'm going to Fourier modes, and define the H-1 norm or any negative positive superlative norm if you want in that way, and that is perfectly equivalent to the usual way, to the usual definition. And here these eigenfunctions have Neumann boundary values. Okay, so in that case, it is quite known, I would say by now, that if we have a Sobolev vector field, what I'm assuming here, that then mixing cannot proceed faster than exponential in time, and the actual rate is proportional to this budget for the velocity gradient. So yeah, I'm assuming that is constant, but that is not really important. Otherwise, you integrate it about one. Okay, so this lower bound has been proved in various papers. The most prominent one is certainly the one by Krippler and Delelis, because they were the first to prove it in the Sobolev case. And it's based via the regularity of the ODE. So Anna mentioned yesterday that the velocity gradient controls the Lipschitz norm of the flow in the case where the velocity is Lipschitz. And what Clipper-Dellez essentially proved that it's the velocity controls like a logarithmic distance, also in the LP setting. This is the underlying idea. There are okay, let me start here. There are direct methods to prove this. They use very crucial tools developed by Clipper and Dellez, maximum function estimates. We talked about, or Anna talked about this yesterday. And there is an alternative way to prove that, and that is based on PDE methods, which do not use maximum function theory. And the first one is by Léger. And unfortunately, he used a black box, 100 pages paper, more or less, which is very, very difficult to understand. Therefore, it's hard to say how these techniques generalize to study situations which are not exactly our model that we're considering. And I'd like to advertise also this result. This is together with my PhD student David Meyer. So here we do a little bit Paley approach to mixing. And interestingly, for the experts, here the maximal function estimate that is the one which fails for p equal to 1, and which is the reason why p equal to 1 is exactly not working, is not used in our approach. Instead, we use the Littlewood-Paley theorem. So the Littlewood-Paley theorem is like the heart of the Littlewood-Paley theorem, in which you decompose your function into dyadic blocks for the wave numbers. And here also the failure of the Littlewood-Paley theorem is not on the level of the velocity, but it's on the level of the transport quantity on theta. So it's kind of the dual problem. Yeah, while here maximal regularity fails for p equal to 1, here the Littlewood-Paley theorem fails for p equal to infinity. Yeah. And my hope essentially was when we studied that, it is based on so you take your transport equation, you convolute it with your modifiers, which are concentrated on these dyadic blocks in Fourier space, and then you do commutator estimates. So you do the proof of dependance. Yeah. And my hope was that we are able to reach p equal to 1 because it works for dependance, but I don't see I don't see for the same what it should be for. Okay, so this is, as I said, I'd like to advertise it because I think it is kind of a different approach, which I don't know, maybe also has potential, and it differs from this approach that we have. Okay, anyhow, examples for exponential mixing. So we have seen the bound, and here are the examples that were mentioned yesterday in Anna. In the BV setting, there are these checkerboard kind of patterns, the self-similar mixing solutions by Depot, Alberti, and Anna. They mixed cats. There's this construction by Yao and Slavish that Andre mentioned yesterday. There are universal mixers. So here I said specific because they work, if you have initial datum, you cook up your velocity and then this mixes exponentially in time. So much progress has been done in the past 5 years by Elgindi, Slatos, and very, very recently Liz and Matting. They construct deterministic universal mixers. So they have a velocity that any initial datum is mixed exponentially in time of it. Okay, so then you have these stochastic universal mixers, stochastically forced fluid models, Alex, Jacob, and Sam, and also, kind of motivated by these results, stochastically alternating shear flows by Alex, Michele, and Richard. And so these results actually rely on the theory of random dynamical systems, which is an ODE perspective, and it's kind of a stochastic generalization of the flow of a vector field. And then exponential mixing is okay. So maybe some will correct me, but I would say it's misspelled here. It's based on essentially Furstenberg's ergodic theorem. I think it's one of the main ingredients. And actually, I was really fascinated by these results. And so when these series of papers by Alex, Jacob, and Sam appeared in the first place, I'm not a stochastic person, so it was very difficult to digest, and I assume that I will never be able to understand it really deep. And so the first thing we did, or the first thing not, but it took some time, but then we started reading seminars. So there's a book by Arnold on random dynamic system. We read it about like half a year or 9 months. Just understand what these guys were doing, and then we read, of course, also some of these mixing papers. But in the beginning, in the end, we don't use clear. Yeah, so that is good. So there are, of course, also velocities which are not exponentially mixing. Prominent examples are steady shear flows. Here, okay, there's so much work on shear flows, in particular by Michele. I really like this work together with Jacob, where they prove enhanced dissipation estimates for shear flows which are allowed to degenerate. And in a certain sense, this vortex that I'm considering is also a shear flow. And it's just that it's not flat, but it's circular. But it's nothing else on the other hand. And these steady vortices were studied by these guys here. And there you always see power law behavior. And actually, what in the construction of Clipper, Luca, and Schulze, you see that the actual exponent might depend on the regularity of the initial data. Okay, so what about the interplay with kappa? So if there's diffusion around, we already talked yesterday about enhanced dissipation. So if there's diffusion, the energy balance is this one. So the rate, there's a square missing here. I'm sorry. The rate of change of the L2 norm is proportional to minus the dissipation. And now, and here this estimate does not see velocity. Yeah, the velocity is just if you integrate by parts, this guy drops out, and this is because the velocity is assumed to be divergence free, so the fluid is incompressible. And if you now do Grunewald inequality, okay, sorry, there should also be a theta. So if you do Grunewald inequality, and then you if you do Poincaré inequality, then you get a Grunewald estimate in which you can integrate, and then you see that the L2 norm is decaying exponentially in time with a constant that is dependent or linear in the diffusivity constant. And this is, of course, optimal for the heat equation. Yeah, I mean, you can compute it explicitly in the Fourier level, and but as I said, this estimate completely ignores the velocity field, and now we have in mind what the velocity is actually doing. The velocity creates gradient, and there's this filamentation. So therefore, grad theta must be very, very large. And in fact, this is also what happens, or what we observe. So in fact, in many situations, the L2 norm is decaying much, much faster. And this is what we call enhanced dissipation. So enhanced dissipation, in my definition, is a decay of the L2 norm with a constant which is much larger than kappa. Okay, so can we say something about bounds here? It's like I explained for the exponential rate of mixing that there are all these bounds available. And the answer is yes. And this is based, I mean, there are two different approaches. The first one is more this direct method that I mentioned, based on like, yeah, maybe unfortunately, Cantor-Rubinstein distances, so Wasserstein distance with a logarithmic cost. And the other one is based on regularity estimates. So if you have regularity estimates, then you can exploit them, and you can show that that the L2 norm decays with a rate, or at most with a rate that is logarithmic in kappa. And this is this estimate, and this is actually sharp. Yeah. So there are deterministic examples. First by Michele, Matthias, and Tarek, which proved that if you have a universal mixer, which is sufficiently regular, so in that case Lipschitz, then you have enhanced dissipation. So, I mean, an exponential mixer on the level of the non-diffusive case, but then in the diffusive setting, then you have you have enhanced dissipation, and the rate is almost this one, but it's I think there's a square root over there, so it's almost up. And I think the optimum one is now claimed by these guys, and in this very recent paper, which I unfortunately not take the time to study. So, and then there are these aforementioned results on these stochastically forced fluid models, and they also get this one. Yeah. Okay, so this is state of the art, and so I'm coming to a new contribution, and I hope that it will become available publicly in like a month or two. So here's the general setup. As I said, we consider a bounded domain, and now we consider Brownian motion inside of this domain. So this red line I wrote here, and we consider in fact a reflective boundary motion in a complex subset of that domain. So we need a certain security radius so that the Brownian motion will not hit the exterior boundary, and when it hits this inner domain boundary, yeah, then it's just reflected and moves backwards again inside of the domain. And wherever the vortex or this Brownian motion is sitting, actually, we are considering the velocity field which is induced by a point vortex at this position. Yeah, so suppose the Brownian motion, so y is the position of the Brownian motion, is sitting here. Then we consider the velocity. So here are the streamlines of the velocity field, which are induced by point vortex. Yeah, so this is what I mean by randomly moving point vortex. And the situation in practice is, it's not just an academic example. It's when you, I don't know, when you're preparing a cake and you're mixing your dough, whatever. That's what you do, right? I mean, you're not sitting there and you keep your mixer fixed at the time, but you do some kind of a random motion. My wife told me, I think that there's a certain shape. Well, it was someone told me that one has to mix it into a certain shape. I don't know. Okay, so anyhow, we do it randomly, and this is what we do. Okay, so but as I said, so now there are two possibilities. Either we go into this direction proposed by Alex, Jacob, and Sam, or, and this is what we do, we rather take a PDE perspective. So we consider the law of this action. So we consider x is the flow of the velocity field, of the random velocity field, and y is the Brownian motion. So we consider the expectation of some initial datum being this should be probably a theta, no? Being I think this is correct. Being affected, being affected by these two flows, the flow and the Brownian motion, and then you can write down PDE. And the PDE for the expectation is just the advection diffusion equation plus the diffusion coming from the Brownian motion. Yeah, this is the standard way that you do. Yeah, you can always go from the PDE perspective to the SDE and backwards. And so now, because of the reflected boundary motion, reflected Brownian motion, F is Neumann boundary conditions. In this new variable here, y is the new variable which comes from the diffusion in the Brownian motion. Okay, so that means, and yeah, I will simultaneously discuss the situation kappa positive and kappa equal to 0. So if kappa is positive, then we of course also have an additional boundary condition, the normal boundary condition for which is in the first. Okay, so this is my operator L. This is the diffusion. This is the operator that acts on F. And here's the abstract result which we have. And the statement is if this operator is hypocursive. Hypocursive means just that I take the H1 norm. In principle, maybe you could also choose another one, but H1 is the standard. If the H1 norm is decaying exponentially in time, then we have almost sure exponentially mixed. And okay, so of course the rate changes, but it's anyhow it's a variable that we don't really control. Or I mean, it's everything. Yeah, you could control it, but we don't do it explicitly. That's why the office is smaller. But they are independent. And the prefactors here also. Okay, so what's the idea of the proof? And the first observation is if L is hypocursive, then also the correlation operator is hypocursive. Yeah, so and here I just mean if I consider correlations, I have to add another variable. This is now I have x1, x2, but I have diffusion, I have the drift in x1 and I have the same drift in x2. And then there's the diffusion coming from the Brown motion. Actually, the reason why this is true is because these two operators, both advection operators, are actually commuting. Yeah, of course, the rates of decay in the norms would change here, but I mean, I guess the correlate, if you consider correlation, then it's just divided by a factor of 2 or something. So that, or if you would consider the, I don't know how it's called, n times correlation or whatever, then input correlation, then it's divided by a factor of 10. Okay, so therefore, okay, so I'm sorry, I have so many mistakes here on the slides. So if F is now this the law of the 2-point process, solves now this PDE with this linear map L2. If that one is hypocursive, then we can turn this into an estimate on the expectation of these, relations. And that is quite straightforward, and it just relies on writing these quantities in terms of F, and then we use Borel-Cantelli to ensure that the largest that there's almost surely a largest M for which this estimate, this point-wise estimate, point-wise in the expectation. Right, and this Borel-Cantelli argument is essentially also at the heart of the earlier.
Just so I understand, so at 0, it's just the advection equation, where U is a point vortex evaluated in the center. WT, where WT is a reflecting Brownian motion.
Yes.
Okay.
So
I don't really understand how it is. But it's sort of vector bias. Okay. I think yes. This seems like something about the PDF of those trajectories, but the original PDE is just transport equation. Right?
The original is okay. I mean, if kappa 0, then this is a transport equation. Then if you go to the expectation, then you get the diffusion generated by the Brownian motion as an additional variable.
The Brownian motion is the same, right?
Why Max?
You have 2 diffusions, right? Plus one and plus net with coefficients. The
Yeah, but I mean, this is the diffusion coming from the PDE. If I consider the advection diffusion equation, so you can drop it.
Right, so if I try to write it in Lagrangian form, you have two branches.
Yeah, that's what I wrote here. If you have a kappa, then you have a different boundary outside.
Yes, the question is the expectation in that is the expectation to expect. So you have to assume they're the same. Right?
No, I think there's
No.
no. I think there's two noises. There's one is the diffusion on the particles. The
Yeah,
other
but
is,
the expectation with respect to each
I think
one.
both.
Yeah, yeah.
I
You're
see.
averaging over both laws.
Yeah.
Because this is a two-dimensional process.
Yeah.
I see, okay.
I guess the wild question is the.
Yeah, exactly. Yeah,
Yeah, no, yes.
good question. Okay, so yeah, that's what I said. Okay, and okay, I do not want to give the details here, but I mean it's essentially it really relies on this estimate where you turn the hypercursivity into this estimate of the expectation, and yeah, this is I think this is basically comes from choosing the initial datum as or from going into this Fourier expansion. Yeah. Or yeah. Okay, so and then here's also now if we want to talk about diffusion, there's also this connection between mixing and enhanced dissipation, which is quite simple, and I will show you the proof on the next slide because it's so obvious. So if the vector field is exponentially mixing, and suppose we've already established this, and here I mean really in the diffusive setting, yeah, because all the estimates, all these estimates, or hypercursivity estimates, were regardless of the diffusion. Diffusion on in kappa, so the spatial diffusion is really just, I mean, it's a course to worry about it, and so if it therefore if this hypercursivity method works for the non-diffusive case, it will almost surely also work in the okay, so and then okay, so if you have exponential mixing, then you also have enhanced dissipation, and I mean the rate that you can compute, so there's some exponential rate, which is of course gamma is smaller than beta. They are both deterministic, and then you have a prefactor which diverges as 1 over square root of kappa. And it has to diverge, yeah, because if we send kappa to 0, we know that the L2 norm is preserved. Therefore, you cannot expect to have anything which is completely uniform in kappa. And I think I already got 2 questions regarding my abstract. That's what I meant here. Uniform in kappa and the rate, not that is actually not possible. Trivial. Okay, so and yeah, you can write it down this way, and then you see in particular the large time behavior. For large times, it's decaying, yeah, with a rate independent of kappa, or you write it down in this way, which uses really the fact that the L2 norm, I mean, that you have. I mean, this quantity for kappa small is too bad, and initially you can do something better. So therefore, this is kind of the initial bound. And yeah, as I said, there's proof that this is off. And here, just to show you, because I mean, yeah, if you're not if you're not so familiar with this problems, then you might it might not be so clear why mixing implies enhanced dissipation. So here's the proof. And I'm so sorry, another mistake. So there's a square missing. So let me go through the proof quickly. So the L2 norm is decaying, yeah, and therefore this quantity must be bounded by the integrated quantity, yeah, because it's decaying, and so its smallest when t is 2 tau. And tau is some random number at this point, arbitrary. This point, okay. Then we can interpolate the L2 norm, interpolate between the H-1 norm and the H1 norm. I use this suggested writing here. And if the H minus 1 norm is decaying, so this is what we use here. So this is this mixing estimate. We always estimate against H1. Yeah? And so then we just have to use Cauchy-Schwarz and do a translation in time. Then we get an integral from t to 2t and one integral from 0 to tau, to tau to 2 tau. And yeah, they're both estimated this way. And now we use the energy balance to estimate the integral against the initial datum over kappa. Yeah, so this is as simple. And there you see already this estimate. And if you want to get the logarithm in the exponent, then you have to use in addition that yeah, you just use the energy balance in addition to get a better form. Right. Okay. So I think I have like 3 minutes only, right? Or when is it?
Yeah, but you can go over by.
Good, thanks. So let's check. Let's talk about this hypocursivity because I mentioned it now, and I have not told you what that means or how it's proved. So let's have a look at this equation again. Yeah? So we have now, we're choosing kappa to be 0. As I said, kappa to be positive. It doesn't change anything here. So, but what you see is if you test with F in the integrate by parts, then you get by the energy balance, you get the Y gradient, and you don't have control over the X gradient. So recall that F is lives on this product space, and you only have control on one gradient. So if you want to see that F is decaying exponentially in time, you would really like to do a Poincaré, but you cannot do it unless you have control over X. And the idea is, well, maybe this L2 norm is not the right quantity to consider, but maybe some other quantity is better. And this is what is often called the augmented energy functional. In fact, we will usually that is what Villani is doing. This augmented energy function is equivalent to H1. And for that one, once you have found that, you prove. So yeah, you have found the right one when you prove an exponential decay in that variable. And once you have exponential decay in theta, and this phi in this augmented functional, then you also have it for in H1 with some prefactor. Yeah. Yeah. This is what you call hypocursive. When this is working. Okay, so here's the abstract result by Villani, and actually we are really checking this for our vector field. The segment by Villani says that suppose you have an operator of this type, A star A star is the dual, and B is antisymmetric, if you want. And then you have to study your commutators. Yeah, so C1 is the commutator of AB, and then you consider these iterated commutators, and maybe there's a remainder, but don't worry too much about the remainder. Yeah. So, and then if these guys are if this is hypocursive, is coercive, then your function in L is hypocursive, and in addition, if the remainder is absolutely controlled. Okay, this is abstract. Here's an example. Let's consider the Kolmogorov flow. So this is shear flow in or quad flow in x direction. Y is linear. So here, the underlying idea is that the smoothness that you get in Y coming from the diffusion is propagated into the X variables. Yeah, and that was also, was studied by Kolmogorov and then more in a more general fashion by Hellmander and led to his hyperellipticity. And actually, Villani's notion of hypercursivity is motivated by this hyperellipticity. So okay, let's see. A is now dy. In 1D, it's also A star. B is Y dx, and you see if you integrate by parts, you get a minus sign, therefore it's antisymmetric. And then if you compute the commutator of these two operators, you see that must be one term in which the Y derivative is falling onto the shear, and therefore this commutator is just the X derivative. Yeah, and therefore if you study A star A times C star C, this is just the full Laplacian. Yeah, and that is of course that's operant. Okay, Remarks. So hyperpressivity was used in the area of mixing before. I mean, in the linear setting introduced by Jacob and Michele, and in many follow-up works by Michele. And as I already said, so you can check immediately if you check the hypothesis that if the original operator is hypercursive, so if it satisfies the Milanese conditions, then also the correlation operator is this is what I mentioned, and that is because then these two guys commute. Okay, and the decay of correlation actually yields the decay of the mixing norm. I should have said this earlier. And okay, so my time is almost over. I can tell you what we are not yet able to do, but which is actually my dream since many years, and I think we're quite close now. So suppose we have a velocity field which is really induced by point vortex, and it has to be smoothed out. Yeah? If you have a point vortex, then the velocity field has is blowing up at this vortex. So it should be smoothed out a little bit. So suppose we consider some epsilon regularization around this vortex. And what is happening if you consider the regularization, because of the smoothness, it is necessary that the velocity goes down to 0 at the vortex. Then it increases until you reach like the order of the regularization, and then it decays. And here you see that the velocity is degenerating. Yeah, so but in one direction only. So the situation is a little bit more difficult than in the shear flow case, where it's really a one-dimensional vector field. So here it's the gradient would degenerate only in one direction. That's a little bit of a problem. Okay. I still believe that's doable because of these results by Jacob and Michele, but yeah, we have not yet figured out the right way to do it. So what we do is we consider monotone monotone decreasing profile, a monotone. Okay, should be increasing. Yeah, so it starts from the vortex, and the vortex is 0, and then it can somehow increase. Whenever we have a profile, velocity profile like this, so always streamlines remain streamlines, then we get the hyperpressivity that we want. Therefore, this is theorem. So if U is a velocity field generated, or yeah, by this changing according to this Brownian motion in that sense, and then U is almost surely exponential mixing, almost surely dissipation enhancing, and just yeah. Reminder: if U was stationary in that case, then it would only mix polynomial. This thing. On where we start.
Any questions? Understand is the 2-point question. Because that there's sort of an inherent bag.
Yes. Yeah.
I didn't see that. Seems to sort of just get
we were worrying about this.
wrapped up in the hypercoursive thing.
Yeah, we were worrying about this as well because it was not, we were aware of that problem, but and I have to say it's not completely clear to me why this difficulty will. I mean, it's kind of clear that once the trajectory, once you have a point on the diagonal, will remain there.
Yeah.
But
That said, was an attracting sense, which shouldn't be. But generally, you have.
Yeah. No, we were a little bit surprised, or were wondering that you don't see it on the PDE level. You do not encounter this problem. It's not completely clear to me why.
Just the strategy is very similar, right? It's, you look at it's more of an dimensional PDE, but such hyperpersivities interesting. Somehow there, you need to construct. Yeah. Yeah. Here's sort of
Yeah, I'm not sure if this is really to do that in our setting, these two guys commute. It's not completely clear to me, because I mean that would probably not be true in your case, right?
Because I think I can say that loosely speaking of the Navier-Stokes version is you get the same flow, but instead of a Laplacian y, it's like a Laplacian dimensional Moore equation for Navier-Stokes. Never showing that operator.
Yeah, so this is a question. We were worried about this quite a while, but we have not. It's not clear to me why this would not pop up. Yeah, so that is for some reason we are not able to do this because of this problem, because of the degeneracy. So if you consider proper epsilon regularization of a vortex, yeah, the velocity has to go down because it's regular. I mean, it's spinning around the vortex, and therefore you have a singularity or discontinuity unless unless the velocity is going down to 0. So if you consider regularization, this is what is happening here. The velocity goes down to 0, and then you have this degeneracy here. The first derivative has a 0 eigenvalue. And kind of we did not know how to deal with this. Therefore, we considered velocity fields, and that's what I meant when I was speaking about a vortex. We consider the same streamlines that are created by a point vortex, but just we flip a little bit the velocity. So that would maybe correspond to having a shear, non-steady shear outside of the domain, which creates velocity to rotate and do to.
But the problem that can be creates. But the velocity at some point has to increase. How do you reach the far? And I think the whole space. You're in the bounded domain. The domain. Whole space you have to assume.
Yeah. Yeah, as I said, so I guess that it should be possible to do that. And yeah, it wasn't. I mean, it was somehow we had this degeneracy always that there were terms which scaled like the distance to the boundary, which we were not able to control by the hyperpersivity. This is maybe a little bit.
But I mean, in this stationary.
I mean, it's stationary, sure. Then it's but. I mean, if it's stationary and sitting, I mean, and then if it's stationary and sitting in the middle, then it's really less like a shear flow.
Yeah, that's right. So I'm just saying in the case of the regular shear.
Yeah, that works. Yeah,
Points,
yeah. Because you only have one direction there.
Correct. Question, let's thank our speaker again. I think we'll reconvene in about 4 minutes or so. I've got your slides, yeah.